Today we'll be having two sessions. First one will be done by Dr. Ruvan, and second will be done by Kaushalya from Learn Asia. So before going into the sessions, let's talk few things. Few interesting things happen in last few weeks in this area. So yeah, first one would be AlphaGo. I think hope you all saw something about that. So, and also AI by Microsoft, and hopefully we'll be able to discuss these things in detail, at least theoretical stuff about these in future events. Just wanted to make some note about these things. You should read some content definitely about AlphaGo because it involves deep learning, reinforcement learning, things like that. If you are into these areas, you should definitely read about these things. And also, pretty interesting use case, AI, what happened to her, or maybe he. And yeah, today. And I saw this very interesting interview with Yoshua Bengio. He's one of the key figures in deep learning right now. And this interview was done by Rework. And this question, what percent of potential future applications of deep learning excite you most? This plain answer was given, natural language understanding. So that's pretty interesting, I think, because there are many use cases like computer vision, fraud detection, classification, clustering. There are many more, but he's really excited about natural language understanding. Why? Okay, I think rather than explaining why, we should invite an expert to talk about that. So our first session will be done by Dr. Ruvan. I don't think he needs any introduction, but for the sake of formality, he's a senior lecturer. He's Dr. Ruvan Weerasinghe. He's a senior lecturer at University of Colombo School of Computing, and also currently serving as the Dean of Informatics Institute of Technology, IIT. And he has like 20 plus years experience in natural language processing. He has done his PhD in natural language processing in 1994. Probably his experience in NLP is older than some of us. So yeah, okay, and he's like well-known academic and researcher, and he has some industry collaborations even with us, WSO2. So, and in areas like natural language processing, machine translation, computational linguistics. So, and also he has a number of publications in well-known conferences, journals. So I think he's the one of the best academics, researchers we can have on this particular area. So let me invite Dr. Ruvan Weerasinghe to do his session. Okay.
Thank you, CD. You would have guessed that he was exaggerating a lot, but seems okay. Okay. I suddenly lost the sound. Can you hear me without this? It's controlling. Okay, thank you. Right. So one of the problems with doing showing something else here. Yeah. One of the problems about getting to something early is that you get stuck in that frame and you don't want to kind of go forward. So natural language processing has kind of been through several evolutions, and today I think some of you are doing some interesting work that I'm learning from. So I just thought of I want to thank CD and those organizers for making me think about natural language processing, because otherwise I don't get time to really think and put down stuff that I've been through. But I just thought that we can start by just thinking of the problem of the human brain. When if somebody gives you 100 numbers, like our brain can't really process this. So we do a lot of things to deal with that. And one is that we want to find out what the middle is, and the other is maybe what the spread is. And these have, of course, statistical terms. And if we have two or more variables, then we want to see whether they are related. So we want to maybe do a scatter plot or something. And then we want to see whether we can model it, fit a regression line or something. And all these are to do with seeing. We want to see. And we don't want to see just the we don't want to see this. We don't want to see this, but we want to still see a summarized version of that. And so we do this kind of thing. But of course, you can have, then someone says, okay, I throw in 1 million or billion data points, and then we have to do something other than just standard deviations and means and things like that. Or they say we have now thousands of dimensions instead of 2 or 3. Then we had to do something else. And I heard an interesting talk by someone who had worked for Johnson & Johnson in the US, where they have thousands of variables, or what you would call dimensions, but a dozen data points. That's another kind of challenge. How do you deal with that? Thousands of dimensions and a dozen data points. It's a different kind of problem. And then, of course, we have data that streams, and this is like one of the really hot areas now. But all that is a different talk, so I'm not going to really, I'm not talking about data, but a particular type of data which is text. So what if this data is text? Can we still take those 100 words and do a central tendency or a distribution? We can't really do much with 100 words, but we'll say 1,000 words. I mean, one document is not 1,000 words, but there are some documents that are 140 characters also these days. But 1,000 words. We can do some visualizations, and most of us have seen those tag clouds, word clouds, phrase clouds, things like that. And then we have kind of millions of words. And it's like collections of documents, and this is formally known as a corpus. Corpus stands for body, of course, a body of text. So this is the kind of thing we do if we have, I don't know, some people do this for large collections also, but that's a slight misuse of this tool. So the famous thing is the State of the Union address by whichever president, so that you can compare all of them and see what were the dominant themes by doing a simple word cloud like this. And then you can see that this is not just a word cloud because it has some phrases in it and so on. So you can do variants on this tag cloud, word cloud idea. And then when you have the bigger documents, the bigger collections, one common thing is to do things, to visualize, what is this document, what is this, is to do frequency. And it turns out that this is a very common pattern, the ZIF curve, ZIF rule. So you see a very few words that have millions, and then very fast it goes down. Another way to see this is if you plot the rank versus the frequency of the word, it is more or less straight line in the negative direction. And So this brings up interesting problems. For instance, so these are some examples of bigrams and trigrams. It brings up an interesting problem. This is an aside. Say if we take 1 million words and plot how many distinct words are there in that, then take another 1 million words and see how many distinct words from all of the 1 million that we looked at in the first. The increase will be very little. And then you take another 1 million words and so on. You keep repeating this. And we should get something like this. You agree? I mean, because we don't have an... So it's actually Zipf's curve the other way. So if you are able to do this, then we can solve this problem. Because nobody knows how many words are there in most languages. I know there is some crackpot who is maintaining the English word count, and he claimed that Web 2.0 was the 1 millionth English word. It was supposed to be the 1 millionth, actually the 999,999th was also a word with a number, and the millionth also had a number, Web 2.0. We tried to do this for Sinhala, and the problem was that it was still going like this, because we only had about 10 million words. So today I think you should be able to collect more and try to, if we can see this curve, then you should be able to have like an asymptote and predict the number of words. I mean, just for fun. I mean, you want to know. I mean, how many different... theoretically, of course, you can do morphology and figure out how many... I mean, you can't really figure out, but you can say this root has so many forms and so on, things like that. So one of the things that preceded this was people... the way people thought they can... process language was to do it the way the linguist told us. And the linguist told that we first do phonology, then morphology, then syntax, then semantics, and so on. But then the higher up that tree we go, we realize that, we have to belong to some school of thinking. We have to buy into a theory. So we didn't like that. We said, no, we don't like that. So language modeling, most linguistics people will leave the room when I say this kind of language modeling. So here we are just trying to estimate the probability of a sentence. And very simply said, if you have a way to count all the sentences ever spoken or written, let's say, written up to now, and then you have this particular sentence, you see how many times that sentence has come before, divided by all the sentences ever written, and that will give you a probability for a sentence. The problem is that's almost impossible to do, so what we do instead is we treat the sentence as a sequence of words where we can calculate probabilities for subsequences of 2 words, 3 words, bigrams, trigrams, quadgrams, things like that. And so today, this slide is very bad, unfortunately. Using those n-grams, we can build a fairly decent language model that doesn't say whether something is grammatical or not. In fact, some linguists are also now considering whether there is a clear-cut distinction between grammatical and not. Because in Sri Lanka, for instance, we say we discuss about things. No? We discuss about a lot of things. In British English, you can't discuss about anything. You can only discuss something. But we wouldn't consider that ungrammatical. That's a usage in Sri Lanka and India. It turns out India, Pakistan, in places like that. So this approach doesn't say right and wrong. It says, okay, this is a bit better than this. Based on what I've seen so far, based on my language model, this sentence is a little better than this sentence. And it's much better than that other sentence. Okay, so just by calculating the probabilities. Okay, so to do all that kind of thing, we need to do the messy stuff, which is prepare the data. And so things like, handling case in the case of Latin languages, we have a thing called case. For most of the languages, we don't have that. No uppercase, lowercase. Word boundary, a lot of people think word boundary, that's very simple, between two spaces. Some languages like Chinese don't have spaces. And also even in Sinhala and Tamil, sometimes you can't do that, even in English. When you have apostrophes and all, don't, what do you do with it? You remove the apostrophe, or you have D-O-N as one word and T as another word, or, so you need to deal with that kind of thing. So tokenizing is not as nice with real data as it is in examples. And the third thing is, of course, stemming and lemmatizing. Basically, stemming is doing something like is shown in this diagram, and you can do it algorithmically and get about 5-10% wrong, of course. So if you strip off, let's say, ing, for instance, for singing it's okay, but for sing, it becomes S. So you need to do some heuristics when you're doing stemming. But you get, most of these data-driven techniques, we expect some error. We never have any data-driven technique that achieves 100%. So if it's 90 plus, we are kind of happy. But only if you do this can you do the kind of things we were talking about before, because otherwise you have an explosion in the number of words, the number of distinct words. So run, running, ran, all those things will be different. And that's not so bad for English, because you get 3, 4, 5 forms of verbs and 2 forms of nouns. Sinhala and Tamil, anybody wants to have a guess? How many forms? That depends, of course. But like in the 10s or 20s or 50s or 100s, or we don't really stop to count. But actually in verbs, it's in the hundreds. And in the nouns, it's in the 60s. So it's really, really important to do this. Otherwise, we are not going to, we will have an explosion in the number of tokens. And the number of tokens, distinct tokens, is the dimension of the problem, as we'll see later. And then we generate some features from this text. 2 common types of features. One is part of speech tagging. So we want to know whether something is a verb, a noun, or adjective, something like that, so that we can do cool things. You can come here. There's a lot of seats up here. So parts of speech allow you to do things like, so I only saw the dog in the text, but I haven't seen the cat or the gharial or something like that, But if I know gharial is a noun, then I can kind of figure out the structure of that sentence. So that's one part of speech tagging features. So you can attach one to each word. And then parsing. I think many of Many people, when you say parsing, they know only of the Stanford parser because it's online and you can try it out. So these are some output from Stanford parser. I just said something like, what are the main tools for text mining or something like that, yeah. And so it gives a phrase structure, a context-free parse, as well as a dependency parse, which in many ways is more useful for high-level processing. So we can send our text through these things and have higher-level features for us to do interesting things about. This is an aside. You can do the same thing of bigrams, trigrams, quadgrams, and so on to characters. And the amazing thing is that you have lots of data suddenly. To collect bigrams, trigrams of rare words is very difficult. So even for Sinhala, we have a 10 million word corpus, but many trigrams are not there. And when you go to quadgrams, they're definitely not there. So, but with characters, if you have a few documents, you already have hundreds of thousands of character n-gram probabilities that you can extract. And so you can imagine that if you have a fairly large corpus, you should be able to generate a spell checker. In other words, if you, we don't know Divehi, that is the language of the Maldives, but if we have their text enough, we should be able to make a spell checker for them without knowing anything about their spelling. If you are interested, you send me an email and I'll send some things on that. So that's just an aside. So then we go into document collections, and we have this idea of similarity. What is, when are two documents similar? Not identical, but similar. So the initial things were like you take the frequencies of words and see whether they are similar. And then people realize that that's not a scalable thing. So people said there are some words that are not important, and they call them stop words. Stop words, I mean, like and, or, and things like that, if, it, and things. So people started saying, okay, we will remove those words. And then people said, still we have too many words to compare two documents. And so they felt, let's take the most frequent terms, most frequent words in each document, and see whether they are the same or they're similar. And then finally they said, okay, that's also not very good, because sometimes, the word president or government comes in everything, in all the documents. So it's not really important in that context. So that's why you have this, you weight the term frequency by the inverse document frequency. That means how rare is it in the other documents. In the document you have the frequency of that word, and how rare it is in the other documents gives it boosts its importance. If it's also common in the others, then it doesn't boost its importance. So this simple idea, and now we have this TF-IDF that is used very, very widely to figure out what are the most important words in a document so that you can compare more easily. Okay, so, and then of course, since this is a very high-level talk, I'm just going to go through these. Bullets are not very interesting, but document classification is one of the things. If you have a measure of similarity, then you obviously have a way to classify documents. And the most common is by topic. But people also have done studies to see, can you detect the author? Did Shakespeare really write that particular thing or something like that? Filtering. Summarizing, okay, summarizing, the more common one is extractive summarizing. So that means you have a whole document with a lot of sentences, and you have a way of learning what are the most important sentences. Most of these are data driven, so you can learn from the data, or you can have some heuristics, such as the first paragraph is really important, and in every paragraph the first sentence is important, and so on and so forth. And you learn some features like that and predict. So your summary will be extracts from the original. The abstractive is the thing people are trying to do. That means the sentence is combining several sentences and giving an idea. So that's still a lot of research in that. And then things like authorship or intrinsic plagiarism. That means, we use, I don't know whether you use, but in universities that can pay, they use a thing called Turnitin. So all the assignments you submit goes through the Turnitin and comes. So they do extrinsic. They're comparing with huge databases and their own collections of student projects and things like that. Intrinsic means you don't need any other document. Within the document, so the motivation is, of course, that a human generally is able to say, especially if there is cut and paste, suddenly brilliant grammar, and then all, or different styles of grammar. But the tricky thing is, how does the human do it? Because you don't know the window size, you don't know the size of the thing that is. So you have to try everything. Sliding window and changing the size of the window. But yeah, so that's another interesting thing you can do. And so that, it was done for authorship detection first, but obvious application is plagiarism. So these are all based on form, the word form, and the part of speech of the word, and the constituent, the phrase of the verb, and things like that, a word, things like that. But if we want to go to meaning, then there was a problem, because the linguists again couldn't give us any help on that. So those people tried to. Most of the treatment of meaning is descriptive, no modeling. So distributional semantics is an attempt to see whether actually the father of a lot of these data-driven things is somebody called I forgot the first name, Firth, F-I-R-T-H. He said, you shall know a word by the company it keeps. Very simple thing, quoted everywhere. You shall know a word by the company it keeps. So if you look at a dictionary for the meaning of table, it will say, I don't know, I haven't checked it, but it will say horizontal surface on 4 vertical legs, or I don't know, something like that. I don't know. So that gives us an idea about what it is, because we already know. If you tell an alien that definition, he's not going to understand. And of course, the computer is an alien. I mean, the algorithm doesn't know anything about the world. So what you say is, you just give it sentences that have the word table. This is, I study at this table, I eat at this table, or, those guys were standing on the table, all the kind of thing, wiping the table. And then you do something like this. Actually, this is called a term document matrix. Term document matrices, so these are all Shakespeare's things, Anthony, Brutus, all these characters, and the books. And it 1 if it occurs, 0 if it doesn't occur. And so term document matrix was the first thing that was kind of, the idea was to see whether how similar documents were. But if you can think of a term matrix, so you have a big collection of text, you take all the terms in on the rows and the columns. And instead of saying 1 or 0, you can actually put the frequency. How frequently did this word occur next to it or within 5 words of it or something like that. And then if you take one of those lines, it's a vector, it kind of defines that word. So table will have things like, high counts of things like food and chairs and, studies in Sri Lanka, things like that. Dog, for instance, will have, very little to do with chairs. I don't know, unless your dog sleeps on the chair or something. But food, yes. But studies, no, So you get the idea. Each of those will be like a signature for that word. So those are called word vectors. And it turned out that when they actually did this and plotted this, for instance, so they found that some unexpected results that, for instance, the dog was closer to the car and things like that. When they plotted this, they found that because the car was here, and the dog was here, cat was up there. So they were like wondering, what, this is not a very good representation until someone drew these angles. When you draw the angles, all things that are like cat come on that arrow. Things that are like dog come on that arrow. And you can see cat and dog are close. Car is very far. And so instead of having Euclidean distance or Manhattan distance, those are the distance measures that are normally common, they said, let's do cosine distance. That means the angle. And so today, cosine similarity is one of the things that I used to see how similar two word vectors are. So that's a two-dimensional thing. Of course, here you will have typically, 20,000 rows and 20,000 columns or something like that. Or you may be interested only in what kind of verbs go with what kind of nouns. And so you may have only the verbs on the column, rows, and only the nouns on the columns. But the important point is this kind of technique is language independent. If we use some linguistics theories, we have to make our models language dependent. So that's one of the benefits of doing this kind of. A lot of people said, we can't do this, the kind of things they are doing for English, we can't do for Sinhala. And that was true. On Tamil, we can't do because we don't have any resources for that. But with this kind of model, you can actually do that. I think, what is my, I didn't set my time, so give me, when it's 5 minutes up. Topic modeling, yeah, so now we have a way to figure out documents, we have a way to figure out the, within quotes, meanings of words, or signatures, I'll say. Not really meanings, but signatures of words. We want to have a way of clustering words in a document, and or clustering documents based on what they are saying. And so topic modeling is a way to actually extract topics from multiple documents. And probably one of the most, if you want, you can think of this also as another feature that we are extracting. So we are extracting a feature for a particular word, life, and that it belongs to this topic 2. A lot of people ask, so what is topic 1? Humans can give a label to the topic 1 because it talks about genes, DNA, and genetic. So we know we can give a title, but actually in topic modeling, it doesn't know that. So the title is gene dash, DNA dash, genetic dash, that whole list. But you can see they are related compared to life, evolve, organism. And the next one, brain, neuron, nerve. And the next one, data, number, computer. So you can induce in an unsupervised way. So we are not telling the system these are the topics. And the system is coming up with topics. And this is actually based on some of that some of the TF-IDF ideas. So after TF-IDF, there's a thing called latent semantics. And based on latent semantics, now there are some new algorithms that are able to do this pretty well. And so we use, especially when you have lots of text, and even streaming text, then we want to be able to know what are the topics being discussed and then follow only the topics we are interested in, for instance. Current obsession is with small document. Current if you think about all the other kind of writing, mostly they are formal books, manuscripts, dissertations, things like that. But these are very informal, and therefore this area has become really important. Subjectivity modeling has many flavors. Sentiment is the most common thing, sentiment analysis, where you just say happy or sad, or maybe neutral. Or you may have like a scale like this one, different levels of happiness and sadness. Or actually this one also has angry and indifferent and things like that. So you may have other categories like that. You may have aspect, that means the entire blog can be negative or sad face, but there may be some things in it that are positive, that are happy face. So that is captured in what is called aspect. So you can say in a product review, for instance, the screen is wonderful, but the battery is terrible, or something like that, in a single sentence. So you have, then if you have the happy and sad, they'll cancel each other. But if you have aspect, then you're saying, okay, the aspect screen is happy, and the aspect battery life is sad. Opinions. So a common thing is now people are trying to, these days they are trying to see whether, from people's tweets, whether they are going to vote for Trump, or we don't know who the other person is now. Intent. So somebody did a project with me, purchase intent. And has a huge marketing value. If you can detect purchase intent by tweets, then you're going to take good leads. You're not just going to advertise to everyone. You take those people who show intent. Personality is another project. So somebody did with me on these big 5 personality types. to try to save from people's social networking, I mean, Facebook, I think it was, what kind of personality they had in this scale. I mean, this is a fairly simple model of personality. MBTI, you get some complicated ones, but this one, since it has 5 categories, got some results. But and there are, like, so now somebody wants to do hate speech, automatic identification, hate speech and things like that. You can have a lot of a lot of things like that. Okay, I think I won't talk too much about this. Information extraction, as you know, is very hot because everybody wants to. They started with named entities and entities, entity extraction, then the relation extraction, then actually populating your knowledge base with RDF triples like Dundee, Freebase, DPpedia. NEL is never-ending language learning. It's a project at Carnegie Mellon or something. So this crawler keeps going throughout the web, and whenever the language is English, it tries to learn usages of English. Watson, of course, is well known, but I mean, I think the biggest thing that flows people is the fact that Watson didn't have a kind of a structured database, and it just basically did the same thing that we do, only thing much faster, reading a lot of books and free text. Okay, I'm going to skip this part because I don't think the speech and machine translation is very important. No? These are the traditional holy grail was like speech recognition and machine translation. So now these are not that they are solved, but people are not so interested in talking about this anymore. I'll come back to that if you want later. Okay, so a lot of the problem we have for English, we have zillions of examples of any kind of document, any kind of data. So if you try to replicate any of those kind of applications in Sinhala or Tamil or some other language, it's not that we want a lot of dictionaries and resources that we are short of, but we are just short of text, raw text. So if you go and look at the tweets and scrape all the Sinhala or Tamil tweets, it's much better than it used to be, but very often it's not enough. So there was a student who tried to do a project to detect the side effects of drugs. And I said, okay, you'll have to select a good drug that is commonly used. And so and the top drug was not Panadol or Tylenol or anything, it was Xanax. And of course he was able to do something because he managed to collect enough only for that drug. So you can imagine if it is in Sinhala or Tamil, I mean, it's very hard to collect lots of data like that. So we are doing things like active learning. How do you learn good models with less data? Similar thing happening to speech recognition for us, Sinhala, Tamil, really hard to get lots of good recordings of people to train. So what we are doing is, okay, let's just train on only one person. The person, the only person who is willing to train enough is the person who is building the system. So you train your voice very well, and then see whether you can use adaptation. So you adapt to another person. That person will only read maybe 20 sentences or 20, 30 or something sentences. That's all. They're not going to. So that's that kind of work. And online learning, I mean, a lot of these algorithms work on batch mode. Machine learning algorithms work in batch mode. So there's a lot of interest in how to convert them all into online so that you can keep learning and you don't have to stop, learn, and then learn in steps, but can you learn as you go? And of course, deep learning, I think CD may be going to have another session on that, so I'm not going to look at this. But a lot of interest, yeah. So most of the problems in speech recognition and machine translation now being solved using these deep networks. Okay, since I talked about seeing the data, seeing the text, I think I should. So most of the standard ways of visualizing text are now being challenged by people are coming up with interesting. I mean, this is a very bad slide, I know. I don't know, maybe I converted it into PDF, so it really got messed up. But you have several other ways of visualizing data to tell the story. Rather than showing frequencies or TF, IDF or doing it there. Some of those are needed for learning models, but for showing and letting the data speak, we now have a lot of new visualizations. I wanted to put a URL there, but so you can't see this, but there are some really good things like D3. I think you have seen the JavaScript library D3 like that. There are some libraries for text visualization that are like thinking about it in a new way, how to show text. Okay, so these just for playing around with stuff. People, there are two big schools, the Python school and the Java school, and now the R school. So generally we can be quite agnostic because we all these frameworks have a lot of interesting libraries that you can use. Unfortunately, R is a little picky because R has lots, but they are not like nicely organized into packages like in Java and Python. But so machine learning, I think you probably have heard of Veka most. That's the most heard of thing. And for topic modeling, you have Mallet or GenSim. And then for visualization, I said I haven't put those here. Okay, so I want to just have a final plug, and that is mandatory plug whenever I talk, the language issue. I mean, we need more people to work with those other languages. Then they have to mess around with Unicode, but now that's not such a big problem because many languages have wrappers to deal with that. There is one problem with our languages, like Sinhala and Tamil and some of them, they call agglutinative. That means they change their form in a very complex way by adding affixes. Affixes means suffixes, prefixes, infixes, things like that. And that causes that explosion in the morphology. So you have to deal with that. And in everything we do, because we are resource poor in terms of, WordNet, that English resource, I think it took Princeton, I can't remember the funding, but massive funding over a decade. It's like the Human Genome Project. So many of those resources have been manually done and impossible to spend on. So we are biased, we need to be naturally biased towards data-driven things. So that's why topic modeling is interesting. That's why distributional semantics is interesting. That's why, so now the Google has this algorithm, word-to-vec, based on neural networks. And it is language agnostic, so it can work with any language. And so we fundamentally need to give enough data that we can learn concepts from. So the right-hand side is actually Sinhala and Tamil versions of the national anthem. Very controversial topic, but I thought it's a good way to finish the talk. If you have enough of this, you can imagine that a human can learn the language. And that's what machine translation does essentially. I think I will stop there unless there is a question on one of those two topics. Thank you. Any questions? Okay, so the question is, when it comes to machine learning, which platform in terms of the operating system? In terms of the operating system, I think pretty much any operating system is okay. You have a different opinion. No, pretty much any operating system is okay. I mean, obviously, if you want to deal with a lot of data, then of course you have to use Amazon Cloud or something like that. But I mean, if we are talking about small amounts of data, then yes. Yes. Semi-supervised algorithm for natural language. Yes, there are some. Actually, almost all these problems have been all tried in using, distant learning and various strategies. In fact, the machine translation is a good example. People tried it with neural nets, then people tried it with the hidden marker models, and finally came up with this so-called IBM model, a very complicated model. Under Occam's razor, we have to basically discard it because it's so complicated. And so we have to prefer the deep learning approach, so where you learn layer by layer different higher level features. So yeah, I think some methods have been more successful in text. In particular, any models that took notice that text is a sequence. Text has a sequence, like DNA. I mean, that's why you can apply a lot of those things to DNA also. So bag of words models, they achieve some things, but some things they are challenged by because they lose that sequence idea. They just don't consider the location. But they have been surprisingly effective in some other tasks, even in language processing. Yeah, so I think, so that's why for many of these tasks, hidden Markov models, conditional random fields, that kind of maximum entropy, that kind of maximum entropy Markov models, those things look at the sequence. So they have been a bit more successful. But yeah, I'm not sure for things like machine learning or, machine translation, I'm not sure whether they have tried anything like that. Yes. I think that's one of the challenges. Sometimes, we do these kind of things. Some student does it and then, I mean, you're also like that. Then it's in the, they either put it on a disc and CD and give it with the dissertation, and it's in the library. More recently, people have tried to start, do their projects on GitHub or something. It's a little more, then there's a little more hope that another person will come and start, extending it. So mostly for tokenizing, I mean, is the simplest task, but it's still an open task because, after I started doing some of this stuff only, I realized that the year in Gieya is not part of the word. In Gieya, the last year is not part of the word. It is actually full stop. That's why you can say Gieya the. The is a question mark. So actually full stop and question mark are redundant. You can't say the without it being a question, and you can't put year without it being the full stop. So that brings, some people in the electronic text, you will find GA space year. In others, it's all together. So then you have to make, fundamental decisions like that. The common way now is to do that text wrangling. You just say space divides my words, and you do the whole lot, and then you do a second round where you say, hey, there's some funny thing here. There are words like ye, ver, ma, something wrong with that. So you have a second round either to combine them with the word that was there, or in some way deal with that. What was the second question? A sentiment analysis? Very good. Because somebody Learn Asia got an interesting problem because the Indian government became very democratic and asked people what do they think about net neutrality, and they got a million responses. So when you're too democratic, you have to spend a lot of money because, obviously you can't read a million, so you have to do some processing, automatic processing before that, at least to see which ones we should read. So recently, our government have this thing, consultation on the constitution. So they told me there are about, I don't know, so many thousand. And so I said, that's much better than 1 million. But then I realized it's in English, Sinhala and Tamil. So that brings another dimension. How do you deal with it? You can have a system for Sinhala, you can have a system for Tamil, you can have a system for English. When you combine them, how do you combine them? How do you weight them and combine them? So a lot of interesting problems. So these are, I wouldn't say no one has tried it, but I'm not aware. Yeah.
Based on all the ideas that you find when you analyze languages, is it not possible to construct rules for making a language, for making a good language? Like Kaushalya not have basically like a rule set for constructing a decent language.
Actually, millennium people came and once asked me, can you design a language that is very easy for our brokers to program? When they say it in that language, it will create a program. So of course I had to say I'm not in the business of language design. That's a completely different area, and that is to do with. But essentially that's what a computer language is. So. And the closest human equivalent to that was Esperanto, but that is, I think, one of the problems with that is that humans, unlike machines, we can't plug that Esperanto chip. If we could have plugged, then of course it's okay. So English is as close as we'll get, I think, to a universal language, unless the Chinese, no, not the Chinese, the Indians kind of expand to 2 billion or something, and then we all have to learn Hindi. Okay, so the question is, when you're subjectivity modeling like sentiment or opinion, how do we kind of do that? And I think a variety of ways. One is, of course, simple, what do you call, supervised learning, where which is very expensive. You get the review or the tweet or whatever, and get a human to say, like, if it's sentiment analysis, the human says, this is positive, this is negative, this is neutral, and so on. The human annotates the whole lot, and you train your model on that, and hope that future data is going to be similar. Okay. Otherwise, you have things called sentiment lexicons, some of which are just -1, +1, and maybe 0 if they're handling neutral, or others that have values. So great will be like +5 or something. Good will be +3. I don't know, whatever. So there are people who have created that kind of thing, and there is even a thing called SentiWordNet, WordNet with the sentiments. So that will be more like not a learning-based thing, but a lexicon lookup thing, and then you kind of try to have a summation. So if you have only -1, +1, then you have a great chance that they'll cancel out and you get 0, when there is actually negative things and positive things. But if you have a graded one, then of course, if the negative words are bigger, more negative than the positive words, small positive words, then it will come out as negative in the end. So yeah, so I think people have tried different, in the case of supervision, they have tried different algorithms, how to learn that. And then people also try unsupervised clustering at the beginning, followed by supervision based on those clusters and things like that, which are not so accurate, of course. There's 2 sources of errors. Okay, thank you very much for listening.
So one thing I got to my mind was like, for these localization projects, probably we should crowdsource. I mean, we recently, in last year, I think we got Google Translate for Sinhala language. And mainly, the main source for this translation was crowdsourcing. So probably we should try that. Maybe someday we'll get something like WordNet. So yeah, that's something just came to my mind. So thanks a lot for the very insightful session, Dr. Ruvan. Wait a second. So we have a very little gift for you for sharing.
Thank you.
Okay, thanks. Okay. Yeah. So we have another session, and it's on kind of different topic, which is very interesting again, and it has some relationship with our topic, machine intelligence. So I would like to invite Kaushalya. He's a researcher at Learn Asia, and he has also published several publications at conferences about big data, machine learning, and social network analysis, topics like that. So today he'll be talking on graph mining and how to mine and model large networks and graphs. So Kaushalya, please. Okay.
Thanks, Edie. So now I'm going to talk about modeling and mining complex networks. So these are basically graphs. A network is represented as a graph. So what is a graph? So this graph theory started with an interesting problem in 1700s by mathematician Euler. So the problem was to find a path. So here is a map. Oh, it is not clear in this one. So here's a map of Königsberg bridges. These are in Italy. So the question was whether a person can go through all those bridges without crossing any bridge twice. So when you are given with a question like this, so people try to solve this with various ways, but no one could solve until Euler tried this. So what he did was he represented this as a graph. So graph is a abstract representation of what you see in nature. So what he did was he invented graph theory. So graph theory, a graph is a set of vertices, those are entities, and they are connected with a set of edges. So an edge represents a connection between two entities. In this problem, it is a connection between two bridges, that is the road. So optionally, these edges can have directions. In some networks, it can be either one way or the other way, and they can have weights also. So we will look at some real-world graphs in next slides. So this network science and graph analysis, these have been there for so many years, but there's a new interest after the web, internet, and social networks. With the introduction of social networks and the internet, so now we have networks with millions or billions of nodes. Like in a social network like Facebook, there are around 1 billion users connected to each other. So we can't do the method that were used with smaller graphs right now with those graphs. So you cannot inspect the connection between two users by just looking at a social network like Facebook, because there are millions of users. So with this, there has been new tech algorithms and new representations are already being done. So there are this new research field. So these are some of the example types of networks. As earlier I talked about social networks like Twitter, Facebook, and even phone call networks. So I'll give you an example in the next slide. Email networks, and there are networks called knowledge and information networks. These are like citation networks. When you cite someone, when you write a paper, you cite others, because research is based on other researchers. It is called standing on the giants. So when you take research papers, they are connected by citations. So that kind of a network is a knowledge or information network, and there are technology networks also. Internet or power grids are called technology networks, and then there are biological networks like protein interaction networks. In gene regulation networks, there are millions of genes, and they are connected to each other based on different roles. So network science is a buzzword these days. This is the field which studies complex networks, and network science is made up from different fields like mathematics, physics. From mathematics there comes graph theory, and computer science also used heavily. Like machine learning is nowadays used in network science, and there are some sociology also used in these things. And understanding a network is a complex process because we have to look at them from different angles. So just by looking at the topology isn't enough. So, and a network is not a static thing. When you look at a network today and when you look at it tomorrow, it can be different. So on a social network like Facebook, millions of users join the network every day, and they make new friends, and some friends are removed, and so a network changes over time. So analyzing dynamic networks is one thing, and studying the evolution of dynamic networks and creating models to represent these realistic networks is another research angle. So these are some of the properties that we use to describe a network. So I'm not going through all of these things. These are just for the sake of completeness. So density, these are size, means the number of nodes in a network, that is in a Facebook-like social network, number of users. And the average degree. Average degree means for each user, how many users are connected to him. Like on Facebook, how many friends are on your Facebook profile. And average path length, that means. So I think I'll talk about it later. And okay, I'll go to next. So here's one interesting data set that we have access through Learn Asia. So we got access to multiple mobile operator data in Sri Lanka. These are called CDRs. So because of the NDAs that we have signed with these operators, we cannot disclose any information about who they are or how many number of users are there. So we can just say we have call detail records. That means if you make a call or send an SMS to someone or you go online, a record called CDR created on the side of the mobile operator. So this kind of data are used in this one. So, and all the numbers are anonymized. That means we don't have the actual number of users, but a new randomly generated number given by the operator. So we don't have any mapping between actual user and this random identifier. So we can say we have at least around 50 to 60% of the users in Sri Lanka, multiple mobile operators. So when you make a call in this CDR data, let's say I'm calling someone like you. So then, and let's assume we are in the same network. So in this one, when I make a call, I connect to my nearest base station, that's cell tower. And then it will contact the nearest cell tower, the nearest one to you, and the call is made. So then in that database, two records will be generated, one from my end, because I'm the one who made the call, and another one on your end, because you received the call. So by using those, we can create a network. So there will be millions of calls, records like this. So because for each and every call, there will be an edge between two users. So this is just a visualization of this. So because it is easier to visualize, I think we are looking at the DSD level, this divisional secretariat division level. So yeah. So these are here, we are just looking at the DSDs. We can represent this as either as users. So it will be difficult to visualize because there are millions of users. Or we can look at the network at the base station level, aggregator level. Or we can, by edges, we can represent either calls, text, or anything. And here we can use the weights similarly, number of calls or the number of minutes. Sorry, there's a mistake. So let's look at some of the properties. These are the characteristics of real-world networks. So if you look at the degree distribution, this is the on the x-axis, that is the number of degree of a node. That means how many other nodes are connected to a particular node. And on the y-axis, that is the number of. So this is in log scale. So when you look at this at log scale, you get something like a straight line. So these are called heavy-tailed distributions. This is a power law degree distribution. So what heavy-tail means, there are nodes that has very high degree. That means there are some users who are having around 100,000 or million users. Like in a social network like Twitter, if you take someone like Barack Obama, he has around more than million Twitter followers. So heavy tail distribution means that existence of that kind of nodes. And these networks are scale free. That means if you take the average degree distribution or anything like that, you can have multiple networks with the same average degree distribution, but they can be completely different when you look at the structural level. So you cannot use that information to represent a network. So this is another one. This is called clustering. So there's a high probability that your friends to be friend with each other. That is the main thing of this clustering, transitivity. So if A is connected to B and B is connected to C, then there is a high probability that A is also connected to C. So that is what shown there. That is the clustering coefficient. So I'm not going into details of how it is calculated or anything. You can check it out. So this is another interesting characteristic of real-world networks. So community is a set of nodes. Those are connected to each other within the group than to the rest of the graph. That means here is this is an artificially created network. So we won't see this kind of networks in real world. Here you can see multiple groups. Those are the communities. In real world, if we can do this community detection, we can identify, if we take a biological network, we can identify the groups based on their functionality. In a metabolic network, the nodes having the same function are grouped together. And even in a social network, there was some similar problem. There was one on Kaggle. They are called ego networks. Identify ego networks. There was some anonymized data was available for some time. In a social network like Facebook, users are connected to each other based on common location, interest, or where you studied. So there are similarities among them. So this is how communities are identified in a social network like this. So there are multiple methods, but here I have mentioned only about modularity maximization. A modularity is a quality measure that measures how good a community structure is. So there are multiple other methods also. The goal of this method is to find the community structure that divides the network into multiple communities, which has the highest modularity. So here's the equation and everything. So this maximization is NP complete. That means you cannot solve it in a polynomial time. So because of that, heuristic methods are used. So let's go into another property. This is called small world phenomena. This became famous with one famous experiment. This was done in 1960s, done by Milgram. What he did was he gave envelopes and a letter. He chose around 300 users, 300 people. There was no social networks at that time. So what he did was he gave those letters and asked each person to give it to someone who knows by the first name. That means friends or peers. So when he did that, he found that each letter reached another person within 6 degrees. That is why it is called 6 degrees of separation. So recently Facebook did something similar and they calculated the average degree of separation for each user. So if you visit this link, you can see your degree of separation. So I had something like 3.29. So what they say around, okay, I think 3.5. Yeah, 3.5 degrees of separation. That means the average degree of separation on each Facebook user is 3.5. So, okay, let's go back to that data set. And we used a method called Ruvan method. That is a modularity maximization method. We applied this on top of that data set, that CDR data set, the call detail records. And at this level, what we did was we looked at the base station level. That means we didn't apply this method on top of the network of users, millions of users, but we had thousands of base stations. So each time you make a call or do anything with your mobile phone, you connect to the nearest base station. So when we applied that method, this is the one we got. But there can be other community structures based on the method or the parameters. So this had 11 clusters, and I have marked the provincial boundaries also. So if you look at that, there are some provinces and the communities which overlap, but the placement of the base stations also play a role. So this shows that people call with others, those who are closest to them. So even you can call anyone in the country, but there is a tendency to call someone who is closer to them. So modularity has some limitations like this, because this method cannot identify communities which are smaller than a certain size. This is famous as resolution limit, and there are some other methods for to solve this problem. And in this method, a user or node can belong only to one community, but in real world, as seen in this one, a person can belong to multiple communities, multiple overlapping communities, like there are family, there are friends, school friends, and where you work. So we have to use other methods to identify those. So these are some recent researchers which have been using machine learning in network analysis. This one is not clear. So this one is finding a low dimensional feature representation. That means right now the graphs or networks are much larger. They have billions of users. So you cannot use that information directly and do analysis. It is not easier because, and they are changing from time to time. So this is, there are several methods to find a low dimensional representation. That means you represent the network with a less number of features. So this is something related to what Dr. Ruvan mentioned earlier. They have used word-to-vec. So they convert the network problem into a natural language processing problem. What they do was they generate random walks on top of this network, and then each node belongs to a vocabulary. That means, as you said, distributional representation. He said, the closer the name, a word can be represented by the words which goes closer. So this is a similar thing. What they have done was they used word-to-vec, which is a neural network-based method done by Google. So they applied deep walk. Deep walk means, in deep walk, what they have done was they generated random walks, multiple random walks, and they did word-to-vec. So at the end of this, what they get is a smaller data set, smaller representation of the same data set that they can operate much easier. So there are other methods also, graph, rep, line, they are similar to this. So, and anomaly detection is another one. This is about detecting anomalies. Anomalies means there are spammers and predators in a social network. Those who are issuing this kind of thing. So anomaly detection, so many machine learning techniques are used, and link prediction, predicting whether two nodes will be connected in future. And another one is information diffusion, like how something will be, some knowledge will be diffused within the network. Like if you are running a marketing campaign, you need to make sure that information goes to most of the users. So this is an interesting problem. Machine learning is used. So these are some of the tools and software that is being used to analyze large networks. So has anyone used any of these? Okay, we use iGraph in analyzing that CDR mobile network, and iGraph has C, basically it's written in C, but there are wrappers for Python and R also. Python one was much slower, so that's why we used R wrapper on iGraph. And there's NetworkX, that's in Python. Giraffe is based on HDFS. It is a distributed processing framework, and PyX is a small one for visualizing and analyzing. And there are some other free and open datasets. So you cannot download a friend network on Facebook, and even on Twitter, there are some restrictions on the number of queries that you can make. So it is not easier to get that kind of data. Once we tried to do that, so it is better if you try this kind of data set. There are so many things, like there are some labeled data sets also. Okay. So, any questions? Okay. You mean the data that we have? Yeah. CDR data, okay. What we get is CDR data, those mobile network data. Those are stored in HDFS. And then we use Hadoop and Pig to convert it into smaller data sets. What we did was we applied iGraph on top of a much smaller data set, like 2 GB or 3 GB. So it was easier to run on one machine. Otherwise, we have to run directly on the cluster, like using something like Giraffe.
Are you using any graph databases?
Right now, no. On graph databases, we are trying to use, okay, we have used Giraffe, so, but then we are trying to use Spark and GraphX also. Currently we haven't used any graph databases, so we are storing as just plain DFS. Any other questions? Yeah, but not on Spark or Giraffe. There are some algorithms like calculating page rank, and on iGraph there are almost all the algorithms that we use. Okay, I think that's all.
Okay, thanks, Kaushalya. I think we learned a lot about graphs and networks. And he was doing this interesting work at Learn Asia, and he has thought that I should probably dig into this more. So he will be joining Murata lab on machine learning. I think I got it right, of Tokyo Institute of Technology this fall as a PhD student. So this will be his last machine intelligence meetup. Probably physically he will not be there for upcoming events. Anyway, I would like to thank him for joining. He was there, he was here for all these events, so he was doing a great job as an organizer as well. So I think you all enjoyed both sessions, and so of course you can talk to our speakers, and of course you can talk with each other and network and get to know each other who are working on these things, who are working on machine learning, maybe network analysis, and also enjoy the snacks and drinks available there. Thanks a lot for coming today. See you again. Bye.